Hello my esteemed viewers. Tutorial. We will go through some of the complex problems in bending moment and shear force uh, variation development in terms of bending moment diagram and shear force distribution diagram. We will take the first example. Of course it is cumulatively numbered, and this is a double overhanging beam with UDL of intensity 20 kN per meter over the entire span, including overhangs. Therefore, the loading is there everywhere and it happens to be symmetrical. Okay, symmetry should be identified with respect to center of the beam, as I told earlier in my tutorial. With respect to center, we have to look aside, that is to the left and to the right, and the loading is symmetrical distance wise as well as intensity wise. Therefore, RA plus RB equal to 20 into 5, it gives us 100, and it will be shared by the two supports. RA equal to RB equal to 100 divided by 2, that is 50 kilonewton. Now we will start computing the shear force values across the span, all along the span. And of course we need to project the important points, and there are 4 important points, 2 supports and 2 extremities. SF at C equal to 0 because this happens to be the free end and it is marked over here. SF just to the right of B is exclusively due to UDL covering 1 meter, therefore it is 20 into 1 minus 20 kilonewton because it is going down, and it is marked over here. So this ordinate value is minus 20, and it should be connected by a straight line because the variation of shear force as far as UDL is concerned is straight line. And SF just to the left of B is the reaction will be included. Now it is going up, therefore it is positive, and here till here there is a negative shear force of minus 20 due to UDL, so it is minus 20 plus 50, 30 kilonewton, and 30 kilonewton is mounted above. See the portion of the shear portion of the diagram above this line of reference, for which about which we are plotting the shear force values, happens to be positive, and below it happens to be negative. And shear force just to the right of A over here, it includes the entire UDL from here till here plus this reaction. Therefore it is 50, the reaction going up, minus 20 into 4, 3 plus 1 is 4. Therefore shear force becomes minus 30, and here it is plus 30 and it's minus 30 when it is connected by a straight line from here till here. Because UDL variation is straight line, it has to cut the center of this particular portion, so it's here. So shear force becomes 0 exactly at the center. And now shear force just to the left of A, even RA is included now. Till then it was 30, minus 30 plus 50, 50 is the reaction, it becomes plus 20, plus 20 is mounted over here. And of course shear force at D should be equal to 0 because it is the free end. So that is also computed, and this is the shear force diagram. And here exactly shear force becomes 0, therefore we need not have to find it out because of symmetry, it crosses exactly at the center. Now as the loading is symmetrical, E where shear force is 0 appears at the center of the beam. Now we will compute the bending moment now, bending moment values, and this point happens to be the important point for the reason that shear force is 0 over here. We have to get the maximum bending moment. Let us see. Now the things are projected, including E also. E is also projected for plotting the bending moment values. Now bending moment at C equal to 0 because it is free end. Bending moment at B equal to minus 20 into 1 into 0.5 owing to this UDL, so that becomes minus 10 kilonewton meter. It's also plotted over here. And bending moment at E, the next important point happens to be 50 into 2.5 minus 20 into 2.5, that is due to UDL. It stretches for 2.5 meters. So 20 into 2.5 becomes equivalent concentrated load into moment Rm is 2.5 by 2. So that takes us to a value of 62.5 kilonewton meter, which happens to be the maximum value among all the bending moment values. It justifiably happens where the shear force is 0. Yeah, it's over here. It is also being plotted. And now bending moment at A, we can come from this end, or we can just gather the value of bending moment at A starting from over here only, from right to left, by covering this particular region. So it is done that way only. But anyway, this is cumbersome. We can calculate bending moment at A starting from here, only taking this particular portion. It becomes 20 into 1 into 0.5. It should be minus 10. So let us see what is the value. So 50 into 3, due to it's a positive bending moment due to this particular reaction, minus 20 into 4. 3 plus 1 is 4. 4 by 2, it becomes minus 10 kilonewton meter. Yeah. Now it should be plotted by a parabola, because the variation is parabolic in nature, and bending moment at D equal to 0 because it happens to be the free end. Now this is also plotted to be a parabola, and while we plot the parabolic variation in any beam, whether it is simply supported or overhanging or cantilever, double overhanging, whatever, whenever we draw the bending moment variations, we should show the convexity upwards. Concavity should not be shown, okay, upwards. It is because the variation happens this way only. Yeah, so this is convexity upwards, and the values are placed over here. This is 62.5, the maximum positive bending moment value at a location where shear force is 0, and this is negative bending moment value, minus 10 and minus 10 over here, due to the symmetry of loading. Now we need to find out where exactly shear bending moment becomes 0, because that point is a very crucial point over the beam, because the behavior of the beam will become different. In this zone the beam will be hogging, and in this zone the beam will be sagging. Therefore there is a contra flexure. See, bending moment value moves from negative to positive, or moves from positive to negative. Anyway, over this particular point, over the span, it becomes 0. Therefore we will take a section. So this is a point which must be located. Therefore we will take a section in such a way that this point is included. We don't know really the distance, but anyway we have an understanding that bending moment at this particular section should be equal to 0. Therefore we will just mark this distance to be x from this extremity, and since this distance is 1 meter, this becomes x minus 1 meter. Therefore we will compute the bending moment value at xx. So it becomes 50 into x minus 1, due to owing to reaction. 50 is over here going up, so 50 into x minus 1 is the moment, x minus 1 is the momentum, minus 20 into x, it becomes equivalent concentrated load, into x by 2 will become the momentum. Therefore it happens to be 20x squared by 2. So if you simplify this equation, it is 50x minus 50 minus 10x squared, and if you organize this equation in such a way that x squared will come to the front, first term, therefore we will it looks like a quadratic equation of ax square plus bx plus c form. Therefore the roots of this particular equation happens to be minus b, so minus of minus 5 plus or minus square root of b square, that is 25 square, 25 minus 4ac. 4 into a is 1, c is 5. So, and upon simplifying we have to get two values for this root. Therefore two distances, one is 3.61 meters, the other one is 1.4 meters. 3.61 meters is infeasible, because it will take the section somewhere over here at this particular junction, because the entire distance is 4 meters. So it will be somewhere over here. Therefore it is infeasible, and we have to assume, or we have to presume, or we have to take 1.4 meter to be feasible distance where bending moment becomes 0. Since the loading is symmetrical, even this distance from here till here also happens to be 1.4 meter. Yeah, 3.61 meter becomes infeasible. Therefore x equal to 1.4 meter is to be chosen. So we'll go for the second problem. Here the problem is a little complex, in the sense there is a concentrated moment applied at the free end, and this concentrated moment is not being applied directly, and there is a frame welded to the beam, and there is a couple that is being applied, 10 and 10. It generates clockwise moment at this particular junction at the free end. So even free end will also rotate due to this free moment of a couple. Okay, therefore the equivalent beam is pictured over here. Only this particular moment is carried and the entire beam is rewritten for the sake of clarity. Now we will take MA, a moment of all the forces with respect to A to be equal to 0. We will get back RB. So it is minus RB into 6 because it will generate an anti-clockwise rotation. So it is 3 plus 2 plus 1, 6 plus 40 into 1. This is 40 into 1, that is the moment arm. 30 into 3 for this particular force, and 20, this is the UDL. 20 into 5 is the equivalent concentrated load, which will be at 2.5 meters from this end. Therefore, since we are supposed to take moment with respect to A, it becomes 1 plus 2, 3, 3 plus 2.5, 5.5 plus 10. The readily available concentrated moment applied over here. It should not be multiplied again by the distance. It becomes a mistake because it is a concentrated moment, readily available moment generated by just welding a frame to the beam. So RB equal to 690 by 6, it will give us 115 kilonewton over here, and RA equal to 55 kilonewton. We can notice RB happens to be big because all the loads are in the proximity of this particular support. Right. And we will go for shear force computation. This is reaction written over here, and we will just move. And anyway, when we start drawing shear force distribution diagram, when we start computing shear force distribution diagram, shear force values, this moment has no consequence. Therefore, let us not worry about that. Shear force just to the left of E is 0, or at E equal to 0. Right, it is 0 over here. SF just to the right of B, that is over here, it is exclusively due to UDL. UDL, equivalent concentrated load, is minus 20 into 1 because it is minus because it is going down. According to our convention, it is negative. It's minus 20 kilonewton. Once again, it is plotted over here and the marked over here, and it is connected by a straight line because variation of shear force is straight line as far as UDL is concerned. And SF just to the left of B, and this reaction will be included. And till then it was minus 20 till just to the right of E plus 115, a positive reaction which is going up, which will give us 95 kilonewton. That's also plotted, and it is just connected. And if you visualize this particular height, it is 95 plus 20. It becomes 115. Equal to the concentrated load, and of course the concentrated load here happens to be the reaction. And SF just to the right of D, we are here, and when we compute the shear force just to the right of D, 115 is to be included, and UDL should be included in its totality. It is 115 minus 20 into 5, so it will give us 15 kilonewton. It is just over here. And when we cross D, when we say just to the left of D, we will have 15 till then minus 30, because minus 30 it is downward force, it will give us minus 15. So it should be connected. So now we can see the step. This is plus 15, this is minus 15. It will never cancel away because we should disregard the sign. We should just compute the height of this particular step. It happens to be 30 kilonewton, which happens to be the concentrated load. Therefore, our plotting is going on smoothly and correctly. Now, SF just to the right of C will be same. It will continue because there are no other forces in between C and D. SF just to the right of C is also minus 15. It's already plotted and it is connected now. SF just to the left of C is minus 15 till here plus 40. So it becomes minus 15 minus 40. It becomes minus 55, which happens to be, it is plotted over here. And this particular height from here till here, this is minus 15 and this is 40. From the total depth from here till here happens to be 55, which is equal to the support reaction. So SF just to the right of A is minus 55. So it is also connected, and this is a shear force diagram: positive portion, negative portion, and negative portion. Right, here there are various points where shear force is becoming zero. It's over here, it's over here. They need not be located because they happen to be falling under very important points. D is located already and the support point is already located. So the values are mounted now: minus 20, 95, minus 15, plus 15, minus 55 and minus 55. Yeah, we will compute the bending moment calculations now. Bending moment at E equal to 0 because it's not equal to 0. It is readily available moment which will rotate this point also in a way the beam hogs. Therefore, bending moment at E equal to minus 10 kilonewton meter. This is a very important thing that we should realize. We should never put it's equal to 0 because even point E also rotates. It also bends owing to the concentrated moment which is directly acting at the point E. Now, so it's over here. Now, bending moment at B equal to this moment negative plus minus another negative moment due to UDL. It is 20 into 2, that is 20 into 2 into 1 because the moment RM is 1. It will give us minus 50 kilonewton meter. It's somewhere over here and it is plotted by a parabolic variation, justifiably so. And bending moment at D is 55 into 3 here. Bending 55 into 3 due to reaction positive, minus 40 into 2, 40 into 2, that is plus 85 kilonewton meter. Right, then it is plotted like this. Bending moment at C equal to 55 into 1. We are coming from this direction. It should be plotted in a straight line fashion, and bending moment at A equal to 0, and this happens to be the point of contraflexion. Now, so point of contraflexion is to be located. Bending moment at section XX equal to 0. We will do it as usually, okay, as we did in the previous problem. So it is minus 10, the readily available moment, 20 into x square, the distance is x, into x by 2, 20 into x by 2, plus 115, the reaction, into x minus 2. So upon simplification, this equation will take a turn like this, and when we simplify in such a way that it looks like a quadratic equation with x square term in the beginning, and we will find the roots to be 2.74 meter and 8.76 meter. Justifiably, really 80.76 is not applicable because it crosses the beam dimension and it becomes infeasible. Therefore, 2.74 is the feasible location where where bending moment becomes 0. Now, 2.76 meter is feasible. Now, draw SFD and BMD for the beam shown, and this is also a typical loading where concentrated moment comes somewhere over here in the center, and it's a single overhanging beam. The loading is not symmetrical, therefore we need to find it out thoroughly. So RA plus RB equal to 80 into 4, the equivalent concentrated load due to UDL, plus 80, the applied concentrated load. Therefore, and we will take moment with respect to A to be equal to 0, algebraic sum of moments, of course. So it is RB into 5, 2 plus 2 plus 1, 5, okay, which is anti-clockwise, plus 80 into 4 into 3, because this is UDL. 80 into 4 is equivalent concentrated load and it acts exactly at 2 meters, and since we are taking moment with respect to A, it becomes 2 plus 1 equal to 3. Here 3 is the moment RM, plus 30, this 30 directly applied moment which is clockwise positive, plus 80 into 6. Here is 80. It possesses a moment RM of 1 plus 2 plus 2 plus 1, that is 6 meters. So therefore RA happens to be 106 kilonewton, and if you substitute RA over here, it becomes 400 minus 106, whatever that we get, it becomes 294 kilonewton. 294 minus 400 minus 294 will give us RA to be equal to 106. So SF calculations, SF just to the left of E is 80 minus 80, we have written, and it is already been plotted. SF just to the right of B, It same thing continues because there are no intervening forces. And SF just to the left of B, this reaction will be included positively because it's going up. It becomes 294. So minus 80 plus 294 will give us 214. So that is also plotted. Now SF at C, here over here, it is 214 till then, minus 80 into 4, 214 minus 80 into 4. Yeah, okay. Now it is plotted over here, and the same shear force will continue till here, and 106 happens to be the support reaction, so our calculations are correct. Anyway, the shear force becomes 0 over here, and this point is to be located because mostly at this particular point the bending moment is going to be maximum. The positive bending moment is going to be maximum, or it is a location where maximum positive bending moment is found. So it is minus 80, 214 and minus 106. Yeah, this is to be located by comparing the similar triangles. We will assume that this distance to be x, and this becomes 4 minus x because from here till here it is 4 meters. So we will compare the similar triangles by taking the ratio. 214 of the big triangle divided by x should be equal to 106 divided by 4 minus x, and upon simplification we'll get the value to be 2.68. Therefore this distance is 2.68. This distance will be 4 minus 2.68. So that point is located, and it is also marked over here because this happens to be an important point. So after drawing the shear force diagram, in most of the questions, of course, most of the problems, we will get another important point over where we need to compute the bending moment value. So here it is, F is here. Now bending moment at E equal to 0 because it is free end, so it's marked 0. Bending moment at B equal to minus 80 into 1 because it is hogging bending moment, minus 80 kilonewton, so it is coming down, it is marked. And bending moment just to the right of D, just to the right of D, because concentrated moment is there. Whenever concentrated moment is there, we should treat, while computing bending moment, the way we treat whenever concentrated loads are present when we compute the shear force values. So bending moment just to the right of D is we should exclude the effect of 30 kilonewton meter. Therefore it is 80 into 3 plus the reaction into 2, that is 294 into 2, minus 80 into 2 into 2 by 2. Okay, that becomes positive 188 kilonewton. It goes somewhere over here. Now bending moment just to the left of D, 188 till then, minus 30 because this is clockwise bending moment, which will make the portion of the beam to hog. So but there is a reduction in bending moment value. It is also shown over here. Now bending moment at F, the very important point, because shear force is 0, it's minus 80 into 3.68 till then, plus 294 into 2.68, the reaction, minus 30, the applied moment, minus 80 into 2.68 into 2.68 by 2, because from here till here it is 2.68. So 80 into 2.68 will give us the equivalent concentrated load due to this UDL into 1.34 happens to be half of 2.68, which is the moment Rm. So bending moment will go somewhere over here. So there is a reduction over here. There is a reduction which is contrary to our expectations because of the arrival of the concentrated moment in between. Okay, there is a relationship between bending moment and shear force, or if and only if the loading is uniformly distributed load or of a particular intensity, then it holds good. The rate of change of shear force is loading, and rate of change of shear force is bending moment. So wherever shear force becomes 0, bending moment happens to be the correct, bending moment happens to be the maximum, but here there is an intervening concentrated moment. That relation no longer holds good. So bending moment at C equal to RA into 1. So we are coming from this side. So RA is 106 into 1, 106 kilonewton meter. Even if we come from this side, which is a laborious work, huge computation we can avoid, then also we would have got 106 kilonewton meter. So bending moment at A equal to 0. So all the points are plotted. Now these 2 points were first computed, connected. This is the next connection. There is a drop, and this drop height you can notice should be equal to 30 kilonewton meter. Okay, at this point, just to the right of D it is 158. Just to the right of D it is 158, and just to the left of D it is 158. 188 just to the right of D, and just to the left of D it is 158. 188 minus 158 will give us the constant intensity of the concentrated moment, which happens to be the 30, similar to shear force diagram. So this is connected, and here till here it should be UDL, therefore it is a parabolic variation, and here till here it's once again parabolic variation, because from here till here there is UDL that is acting. So therefore we got one point of contraflexure which is to be located. So therefore we take a section over here such that this particular point is included from this end, and we mark this distance to be x as usual. So point of contraflexure is to be located, and it's here. Now minus 80x, that is due to this concentrated load, plus 294 is the reaction. 294 into x minus 1 equal to minus 80 into x minus 1, this portion of the UDL, that is this portion of the UDL that exists in the distance x minus 1. So 80 into x minus 1 is equivalent concentrated load. X minus 1 by 2 is the momentarum. Therefore the entire relationship at xx, the bending moment value happens to boil down to this particular equation, and when we simplify it is equated to 0 because bending moment at that section is 0. Now we will get the roots to be 1.25 to be feasible solution, because the other value happens to be 5.10 meter, which is infeasible. So with this we have done 3 problems which can be assumed to be little complex when compared to the problems that we did in the previous tutorials. So next tutorial will come up with further complicated questions on bending moment, and later on we will move for bending stresses and shear stresses in the beam. Until then, bye, and if you have liked this video and if you are not yet subscribed, kindly subscribe to my channel.